Okay, good evening, everyone. I think we can start. I'm just not sure if the guys for primaries are all here. I mean, are you all guys here? Hello? Can you hear me?
Yes, Doctor, we can hear you.
Okay, sure, thanks. All right. And then can I also ask the person identifying as Zoom user to change to their real name, please, so that we can know who's here. Okay, thanks. So we'll just do the anesthetic machine, mostly the physics of it. So in anesthetic machine, people always think that the person who came with the machine or who invented the machine is Henry Boyle, but not really. When he made a Boyle's machine, there was already existing machines. So he he built from something. But there are also but mostly the machines that we use now are modifications from the Boyle's machine. So really the function for an anesthetic machine is to receive compressed gases from a supply source. We'll talk about the supply sources of gases. And provides continuous and constant flow of gas mixture of known composition and flow at a common gas outlet. And then it will also help mix the gases and also the vapors that we use. And with that, you can incorporate ventilation. And it's also safe. Let me not say it's safe. It minimizes risk to the patient and the staff. By the end of the TAT, you will know how this happens. So the basic elements of an anesthetic machine are a high pressure supply or a high pressure system, pressure gauges with their pressure reducing valves, flow meters, that can be metal or glass, vaporizers, and then a breathing system. There were other things that I didn't put here is the scavenging system. So from the guys writing primaries, can you please tell me how an anesthetic machine is divided? Anyone? Can someone tell us how an anesthetic machine is divided?
All right, one. By
Sure.
division, yes, by division, do you mean, or I think, let me just answer the question. I think it's divided into high pressure system, intermediate pressure system, and the low pressure system in terms of the pressure system.
Okay. Okay, good. So what comprises of the high pressure system?
So then the high pressure system would be mainly the cylinders, which are located at the back of the machine. And
Okay.
then the intermediate pressure system would then be the pipeline gases. And then the low pressure system is then the flow meters, from the flow meters.
Okay. All right. That's fine. Thanks. So you can divide it into two or three, whatever works for you. but intermediate tends to overlap with low pressure system. So that's why for me, it works for me to just divide it into high pressure system and a low pressure system. So like you said, the high pressure system is made out of the cylinders, the manifold, if that's the supply of oxygen or air, and also the pipeline system. Then at the back of the machine, there's a yoke. We'll talk about the yoke. There's a pressure gauge and also a pressure reducing valve. Those make up the high pressure system. Then what divides the high pressure system from the low pressure system is flow control valve. So they will divide these pressure zones. So with the low pressure system, it's the flow meters. Some call them rotameters, still the same thing. Vaporizers, flow control valves, and then the common gas outlet. So that's how you divide a machine. Even like I said, even if you want to divide it into the intermediate system, you can, but most texts they talk about high pressure and low pressure system. But I don't think anyone would question you if you divide it into three. So just to put it in a form of a diagram, remember we said the flow control valves, they separate these pressure systems. So this side will be the high pressure system. So cylinders, pipeline or manifold, which is also made up of many cylinders. It will then be divided by the flow control valves into the low pressure system. So the low pressure system, we said, is the common gas outlet, vaporizers, the flow meters. Some people will call this the intermediate system, like Dr. Fuchane has mentioned. Can anyone tell me what is a manifold and how it works? Remember we said the sources of gas could be manifold, cylinders, and pipeline. How does a manifold work? Let's talk about manifold for oxygen. What is it and how does it work?
No, I can't take a picture. Jesus Christ.
Dr. Majuna, can you talk or are you busy? So a manifold, just to give you an idea, so that I don't trick you, a manifold is what we use in Bedford, if I may give you a clue.
Doc, is it not the cylinders, the larger cylinders which are connected? Is it in series or in parallel, which are usually situated outside? It's for smaller hospitals.
Yes.
So it's basically those
So with
black
that one,
bigger cylinders.
yes. And if you notice, you'll find that maybe 3 or 4 are connected at the same. So the 3 are combined, and then maybe it's 8, but divided into 2. So 4 will make one system, 4 will make one system. So once one will be supplying at a time. So once a pressure drops to a certain amount, there'll be an alarm that will go off. So someone has to come and switch it such that now the full cylinders can supply while they replace the empty cylinders. So you always have 4 cylinders as backup when the other ones they run out. Some systems have been made to be automatic such that when the pressure drops to a certain number, then it will automatically switch to the full ones. So that is what is called a manifold, and it's you rightfully mentioned that it's used for smaller centers, and also, yeah, if there's not a lot of oxygen demand. Which type of cylinders do they use for manifold?
I think the J cylinder.
Sorry? I didn't get that, sorry.
Is it not J cylinders, Dr. Suba?
Yeah, it's the bigger ones. I to be quite honest, I always mix them up. If it's not J, it's H cylinder. Yeah, it could be J, actually. J. Yeah, it's J, I think. Well done. Okay, thanks. So, we were there, sorry. So, it's just the same thing, that the low pressure system is made up of flow meters, vaporizers, check valves, and also common gas outlet. And then the high pressure system is everything else that we've mentioned. Then this can be intermediate. And they also like asking what separates high pressure to low pressure. So it's the flow control valves. So the power supply for our anesthetic machines, it's responsible for the ventilator part, for the monitor part, and it has to be continuous. You have to have a backup battery that can last for at least 45 minutes and above, so that at least if there's a power outage or power failure, then while you're trying to sort out the patient, then you don't struggle. So that is why an anesthetic machine should always be connected to uninterrupted power supply. So there are plugs in the hospital that even if power goes, or as soon as the UPS kicks in or backup kicks in, then those plugs will have power supply. So just keep that in mind. And then how else can gas? Okay, never mind. Let's continue. So the gas supply, like we said, is required for continuous flow of anesthesia. So the pipeline will have a pressure of about 4 bar. So that one is from the 4 bar will be from the VIE, which is, what is a VIE? Is Dr. Kobinga here? Or Dr. Georgios, can you answer? What is a VIE? What does VIE stand for, and what is it? Who is APCT now? Okay. Oh, Dr. Georgios is on call, sorry.
Hi,
Dr.
Dr. Scott.
Banzana? Oh, hi.
So VIE, doc, stands for, I think it's vacuum insulated evaporator. So
Okay.
it's what we use, I think, to store some of the gases that are delivered via the central gas supply, doc.
Okay.
Hello?
So, okay, and how does it store the oxygen? Okay,
So
you can talk open. Yeah.
oh, there's a lot of noise. I'm so sorry. So I know that it's stored in liquid form. I just don't entirely remember the whole flow process, because then I think at some point it's then converted to gas, but it's stored in a liquid form in the VIE. So it's cooled down to liquid.
Okay, that's fine. Dr. Anis, you had your hand up. You can talk.
Oh, I was gonna add on what you were saying. Basically, it's a vacuum. It acts like a flask, whereby there is insulation, which protects the temperature, which is in the core, which is about minus 160 degrees to the outside. So this helps oxygen to be kept below its critical temperature, which is about minus 119. So you find the
Good.
oxygen is inside there in liquid form, and then just on the top of it, you find the gaseous form of oxygen, which is the one which goes out to the pipeline. So this oxygen needs to be continuously used so that there's no buildup of pressure from that oxygen, which is continuously flowing because of is it latent evaporation. Yeah, I
Yeah,
think so.
so if the pressure builds up,
So, yes, there's a pressure releasing valve. If you stay, they say for about a week, if it's not used for about a week, the pressure builds up a lot such that the releasing valve has to release oxygen into the atmosphere. So there's no explosion or something from the pressure buildup. So
okay,
basically,
and
this
then what
oxygen,
happens if, okay, you can finish, sorry.
as it is released, it loses a lot of temperature. So it's very cold when it gets into the pipeline. So it needs to be warmed up. So there is usually a super coil which warms it up to normal temperatures before it gets into the pipeline. And also there are some pressure relieving valves which drops the pressure from is it 700, then it goes to 10 and then goes to 4.
Yeah, something like that.
Mm.
Then the other question they like asking, if there's underuse of oxygen, what will happen to the VIE? How will it compensate for that? If there's overuse of oxygen, how will the VIE compensate for that?
Okay,
That's
so
for you, Dr. Anis.
we said for overuse, because the oxygen which is released gets very cold. So the more you use it, the colder it becomes. So you have to actively warm it up, or otherwise the oxygen will get to the patients very cold. That is from overuse. From underuse, we said there will be pressure build up, such that if the pressure releasing valve does not release too much pressure in that cylinder, so that pressure releasing valve into the atmosphere is also important for underuse. So it's very important. This one is called the continuous use of oxygen. So it has to be always in use.
Yeah, well done. I'm really happy with that. So also, if you are overusing it, the supercoils, they will heat up the liquid oxygen so that it evaporates to gaseous form. Then you've got more oxygen available to go through the pipeline. Well done. I'm happy with that. So if you're writing primaries, you need to know about gas supply. Okay, so like I said, when it gets to the back of the anesthetic machine, it's at 4 bars. So 4 bar, then so that is from the VIE, but with the manifold, how much will it be, Dr. Banzan? How much will be what's the pressure of an oxygen? Oh, sorry, I didn't see that I wrote it. So can you see that for pipeline pressures, you don't really need a regulator or a pressure reducing valve, but for cylinders you do, because you see it's 137 as compared to 4 bar, 137 bars. So, and then this pipeline will connect to the back of the machine via a non-interchangeable screw thread system. And then you also need to have backup cylinders at the back of the machine. So one will be connected to the machine, one will be in theater ready for use. And then, like I said, that it's how you connect to the back of machine is gas specific, non-interchangeable screw thread, and also it's color coded. And also there are Bordon gauges that help to indicate these pressures, whether it's for cylinder pressures or pipeline pressures. So we'll also talk about these components as we go. Okay, so as you can see, this is a back of an anesthetic machine. This is from the pipeline. So this is connected to the wall and also to the back of the machine. So this is for nitrous because it's blue and it's non-interchangeable screw system. And then also at the wall level, it's the diameter index system and also the shape index system. And then for medical aid, it's blue, and also then oxygen is here, it's cut off, it's white. And then also these pipes can withstand a lot of high pressure. You can't kink them. They're very, very hard. So it's also a protective mechanism. So that's how, and then also this is the yoke, and this is how you connect your cylinder. This is an oxygen cylinder connected via the pin index system to the back of the anesthetic machine. So this is how you supply gases to the anesthetic machine. So we've talked about the pipeline system, how you connect to the wall. We already talked about it. So it's color coded, diameter index, and also shape such that you can interchange them, and also the pipeline that is non-kinkable and also color coded. And then so yeah, we've already talked about the non-interchangeable screw thread that connects to the back of the anesthetic machine, also as a safety measure. Then we have this Bordon gauge, which with these are like, so they monitor pressures, especially pressures for cylinders and also pressures for the pipeline. So who can tell me how a Bordon gauge works? How does a Bordon gauge work? Primary guys?
Hi, Dr. Six. Can I try? So how it works
Yeah.
is that so when there's flow of gas which goes in through the socket, right? So we have the bottom tube which straightens out and curls or goes back to the C shape depending on how much pressure there is. So when there's like high pressures going in, it'll go through the bottom tube and it straightens out. So in turn, it will sort of like pull on the adjustable link, which will then also pull on the pivot, which will then adjust the marker depending on the amount of pressure there is on the tube. So when there's increased pressure, it straightens out, pulling on the adjustable link and the pivot, in turn the marker, then it'll give you a reading on the scale. So when there's low pressures, it sort of goes back or reverts to the C shape, which will then turn the marker, I think, anti-clockwise.
Okay, good. I'm happy with that. So as you can see, this part goes to the cylinder. So as you're saying, the tubing, the other side is open, the other side is closed, and it has this link which is connected to this system, and there's this needle marker. So when pressure increases, or when there's high pressure within the, take an example of a cylinder. When there's high pressure within the cylinder, this will straighten out and pull on this link. When this link pulls, then this system will move. And as this system moves, and then this will also move, and it will indicate if your cylinder is full or it's getting empty or whatever. So that's the needle. So we get to see this needle pointer, but we don't know what happens behind it. So that's how it works. So this side is open, this side is closed, but it's connected to a link that is also connected to this system where it has a spring and all in this needle pointer. So as the pressure increases within this tube, then this thing will tend to straighten out and pulling this link, and it will move this needle. It will move this whole system, but we'll see this needle pointer moving. It also has some safety mechanisms. It's also color coded, like you see on the anesthetic machine. It's also gas specific. And then who can tell me, one, the question is the Bourdon gauge connected to a nitrous oxide cylinder reliable? If yes, why? If no, why? Can you explain the physical principle against that?
It's not reliable, Dr. Sukan, because
Okay, why?
it's not reliable because of nitrous oxide that is being stored as a liquid and also as a gas. So what happens is that the Bourdon gauge will only detect when, okay, so the pressure from the vapor will still be the same despite the changes in the liquid. So it's only after you have just almost completely ran out of the liquid form that you will see the pressure also going down. Unlike oxygen, when you use it up, you can see that half oxygen will also be reflected on your gauge. So you need to weigh the nitrous oxide in order for you to know how much you have.
Okay, thanks. You guys are making me very, very happy today. Well done. That's exactly that. The reason it's not reliable is because in the cylinder, nitrous exists in both liquid form and gaseous form. The reason for this is because nitrous oxide evaporates at room temperature. So that's why she's saying the pressure will be constant at a certain number until the liquid form runs out, and then you only have the gaseous form. Then it will start moving as you finish that one. The best way to monitor it is with the pressures and also weighing the nitrous oxide cylinder. I hope that makes sense. Otherwise, well done. I'm really happy. So that's the Bourdon gauge. So remember, we spoke about the yoke, which is the back of the anesthetic machine. So its function is for orientation and also to support the gas cylinders. It also has a buttock seal, which helps to avoid leaks. So it gives you a very tight seal. And it also ensures unidirectional flow of gas so that there's no back pressure or backflow. And because it's gas specific, it also prevents giving a hypoxic mixture of gases. And it's incorporated with the pressure gauges and also pressure reducing valves. Remember, we said from cylinders, you get about 137 bar, which is very dangerous for the machine and also for the patient. So you have to have the pressure reducing valves and the Bourdon gauges incorporated into the yoke to also monitor and reduce this pressure. So so this is the yoke. It's something like this. And we've already mentioned its functions: supports the cylinders, tight seal, allows unidirectional flow, and prevents cylinder. So it prevents you from giving a thingy, a hypoxic gas mixture. And it also has this Bourdon seal. It looks like this. So the way you connect cylinders to the yoke, it's via the pin index system, such that the pin index system for oxygen will not be the same as for nitrous, will not be the same as for medical air. So for oxygen, it's 2 and 5, which, as you can see here, but for nitrous oxide, it's 3 and 5. They like questions like this in the multiple choice. So these are giveaway marks. I know when you're reading, it can be something that you just overlook and move on, but they can just give you a multiple choice question and wanting you to identify the pin index system for nitrous, pin index system for oxygen. Okay. So the pressure regulating valves now, or the pressure reducing valves. If you remember in the beginning of the chart, I did mention that pipelines, the pipeline system will not need pressure reducing valve. But if you're using a manifold or a cylinder at the back of the machine, you need to reduce that 137 bar to about 4 bar. And it will also, the pressure reducing valve will also help to provide constant flow of gases. This is protective to the machine and also to the patient. And yeah. So to understand the physics behind the pressure reducing valve, you have to understand this formula that force equals pressure multiplied by the area. That's how pressure reducing valves work. That's the physical principle behind that, sorry. So I'll also ask someone to explain briefly to us how, using this diagram here, how a pressure reducing valve works. And based on that formula we just showed. Who wants to attempt? Hello?
I think, can I attempt?
Sure.
So you're gonna have high pressure inlet. So you're gonna have your gas flowing in through that high pressure inlet. And then on that high pressure inlet, yes. And then so it's gonna push that what is that thing? So it's gonna push it up with the spring, reducing that area around. I think it's gonna reduce this area around where you could see from the high pressure to the A. So then you're gonna have less gas going through into the low pressure system.
So,
but then if there's low pressure, then the spring will be able to relax and opening that area to allow more gas to flow. Things like that.
okay. All right, thanks. So just to break it down a bit, the components of the pressure reducing valve, as you did mention that it has this high pressure inlet this will be coming from the side of the manifold or cylinders. Then there will be an outlet once the pressure has been reduced. That's why it's called a pressure outlet, low pressure outlet. Then this is the diaphragm, which is the area mostly. This is the diaphragm. And then this is the spring, which is also a force. So this tends to push down. And then, yeah, those are the main. So you've got two forces happening in a pressure reducing valve. This force from the spring pushing it downwards, and then this force from the high pressure inlet pushing the diaphragm upwards such that the pressure evens out and then you get a lower pressure. That's how it works. So you've got two forces applied at the same time. Then as pressure increases, the diaphragm is pushed up like this. Or if the pressure from the spring is higher than this one, then it will push it down. And then usually it's constant pressure. It's set such that you get about 4 bar. Because you know how much is coming here, you know how much is coming here, then it will even out or cancel out to provide a certain pressure that you want. In this case, it will be 4 bar. So it comes here as 137. You've got a force applied here, you've got a force applied here, and then you reduce that pressure that was coming here via this to a low pressure of about 4 bar, which is usually constant. So just remember that there are two forces happening at the same time to try and reduce the pressure such that you get a low pressure system. Is that clear or it didn't make sense? Okay, we can move. So we already mentioned how this works. I'll skip that. Pressure gauges, Bourdon gauges we already mentioned. So we'll skip that. And then there are also flow meters or rotameters. These will help to now you are inside the anesthetic machine. They will help to reduce the pressure from 4 bar to just above 1 bar, which is about kilopascals. Sorry, that's a typo. It's supposed to be kPa, no, not kPa. So that's what the flow meters will do. So they will help you to reduce the pressure from 4 bar to 1 bar, which is about 101 point something kilopascals. So you can't give 4 bar to the patient. That will cause barotrauma. So the flow meters or rotameters, their properties are constant pressure and variable orifice. I'll explain just now what that means. And then inside them, there's a ball or a bobbin, which will move proportional to the gas flow with a tapered glass tube. By tapered, it means that it's wider at the top and then it's narrower at the bottom. So that's why it's called a variable orifice. So the flow inside these flow meters, it's dependent on density and what type of flow and also viscosity. So obviously at low flows, you've got laminar flow, and now the flow is mostly dependent on the viscosity of the gas. Then with high flow, you've got turbulent flow, and then the flow will be dependent on the density of the gas that flows through it. And these rotameters or flow meters are calibrated for a specific gas at a specific atmospheric pressure and temperature. So at sea level, they are calibrated differently than at higher altitudes. So just keep that in mind. And you've got flow meters for oxygen, air, and nitrous oxide. So remember we said it's a tapered gas. As you can see, it tapers off. The inside lines, can you see they are tapered? At the top, they are wider. At the bottom, they are narrower. This is the bobbin. It's open inside it. So as the flow goes through it, it will start spinning and raising according to the flow. You start looking at the flow. So it's not the middle of the bobbin that will give you the flow rate. It's the top of the bobbin that gives you the flow rate. And then it also has anti-static material that will prevent this from sticking to the sides of this. So just keep that in mind. I think that's so you can turn it clockwise or anti-clockwise. So when you turn it clockwise, you're opening it. When you're turning it anti-clockwise, you're closing it. Then there's also a sequence of how this should be in the anesthetic machine in terms of oxygen, medical air, and nitrous oxide. We'll talk about that just now. So they are also for safety features, for our safety measures, they are color coded. And the size and shape tends to differ. So for oxygen, it's larger and it's octagonal in shape. Don't ask me how does an octagonal shape look like? And for oxygen, it projects out further as compared to the other rotameters. In the UK, the rotameter will be located on the left side, and it's separated, and oxygen should be the last to be added to the mixture such that you get to the common gas outlet. We'll also explain why as we go. And then also there's nitrous cut off. So it means that if oxygen fails, then nitrous oxide will be automatically cut off. And also such that when you open nitrous oxide, the rotameter for oxygen will also start opening to a certain flow, so such that you don't give a hypoxic gas mixture. Like I said, it also has anti-static material such that it doesn't stick. And then the bobbies rotate to provide the visual confirmation of flow. Like I said, it's the top of the bobbin, not the middle of the bobbin, that gives you the flow rate. So yeah, can you see? So that's what I was meaning. So here it's off because the bobbin is not spinning, and also it's at the bottom. But as you open it, it will start raising. And I did mention that it's not this dot that will help you to know the flow rate, it's the top of the dot that tells you, the top of the bobbin that tells you about the flow rate. And then the hypoxic guard, we just mentioned that oxygen and nitrous control valves are linked mechanically such that if you open nitrous only, the oxygen will start going up also. And then if you that's that. And then also if there's an oxygen failure, then there will be a cutoff of nitrous oxide. And in terms of sequence of how the gases are added into the common gas outlet, oxygen, like I mentioned, this is the correct one. The oxygen should be the last to join the common gas outlet. These are the reasons why. Imagine if it's the first to join the common gas outlet and there's a problem, there's a leak or a breakage, you see some of the oxygen will be lost without going to the common gas outlet, and that will give that way you can give a hypoxic gas mixture. If it's in the middle, some of the oxygen can go this way, then you dilute the oxygen and you can give a hypoxic gas mixture. But if it's nitrous oxide that's lost, I'm sure that's not dangerous. As you can see. So always oxygen last to join the common gas outlet, and it should be in this position to achieve that. So vaporizers, I will not talk about vaporizers because it's a topic on its own, and that would make this chat super long. So I'm sure a chat on vaporizers is coming. I also believe Dr. Madavane did give a nice presentation on vaporizers that I think was sufficient for you guys writing primaries. Then we get to the oxygen flush. So with the oxygen flush, it's really just an emergency oxygen supply. I hardly ever press this thing because I just feel it's too dangerous. So when you press this oxygen flush, you are bypassing the rotameters and the flow reducing valve, and then the rotameters, and the back bar. So if you're using pipeline, it means you're giving the patient about 4 bar of oxygen at a pressure of 4 bars, at a flow of about 35 to 50 liters per minute. You can see you can cause barotrauma, and if you are giving volatile anesthetic agents, then you will be putting that patient at risk of awareness under general anesthesia. So that is why people will say when your bellows collapse, you must press the oxygen flush. There's no need for that. You can just go up on the flow until the bellows start moving again and they're full. Then you can start to come down again on the on the on the on the flow. Some people also talk about it when if you bag mask in a patient that is difficult airway, then you can consider using it. But generally, I try to run away from it for these reasons. APL valve, the adjustable pressure limiting valve. So this one, it forms part of the breathing and also the scavenging system. So it helps to alter the pressures within the machine in a patient who's spontaneously breathing or manual ventilating when you back masking the ventilation. So practically, when you set the pressure to be 20 centimeters of water, this valve will start to open once the pressures are at 20 centimeters. So it will pop off when or vent off some gas when the pressures are above 20 centimeters, but below 20 centimeters of water, it will not do that. And this helps to protect against barotrauma. But obviously, when you're pressing on the valve, that can cause barotrauma. So as you go up, if you increase it to 30, it will vent off gas at 30 centimeters of water until you get to 70. And then the maximum we know that it's 70. That's your APL valve. So it's incorporated into the breathing system and also the scavenging system. And then with low flow anesthesia, I thought it was nice to just touch on it. So you need a circuit, you need a CO2 absorber to do it. The other things that you need an oxygen sensor in the inspiratory limb. You need a circuit pressure monitor. You need an expiratory valve. You need an inspiratory valve. You also need gas analyzers, which is CO2, oxygen, and also your volatile anesthetic. And also you need a water trap. So we say you are giving low flow anesthesia when you're giving a patient flows of less than 1 liter per minute. This tends to be cheaper and also helps with less pollution for the patient. So this is if you're using nitrous oxide and also volatile anesthetic agents. But if you're doing TIVA TCI, there's really no need for low flow because you will be wasting the CO2 absorber. You can just run high flows because there's no nitrous, there's no volatiles that have toxic byproducts. Then coming to the scavenging system, it's mostly important for the nitrous oxide and the volatile anesthetic agent. We need to find a way of getting rid of them. So a scavenging system is connected to the APL valve and also to the circle system. So there are two ways that you can have a scavenging system. It can be active or passive. With active, the outside you generate a negative pressure using a fan so that you can suck out the waste. So it's called subatmospheric pressure scavenging system, where there's a fan that will suck out the waste. But with passive, there's no fan. You just want these gases moving from a region of high concentration to a region of low concentration, and then later they are dissipated into the atmosphere or into the environment. There is a pressure relief valve such that you can't get this negative pressure to the patient. So the flows are usually at 75 to 130 liters per minute. So the components of the scavenging system, it's about four components, sorry. So there's a collecting system, as you know from the anesthetic machine, that the scavenging system will be connected just next to the if you're in theater, you can check. It's next to the bellows and also next to the soda line. So that's where it's connected. So that's called the connecting system. And then The transfer system is the tubing now that is transferring the waste from the anesthetic machine to where it's connected, close to the pipeline system also. Then the receiving system, we usually don't see it. So the receiving system or the reservoir system, it's open-ended and it has bags and valves that prevent this waste going this way. So it just keeps it there. And then now, whether it's active or passive, if it's active, then there'll be a disposal system here, where if it's active, there'll be that fan generating negative pressure, which will suck the air out through this way, or passive, where there's high concentration of the gases, and then they'll move to the environment where it's lower concentration. So that's the disposal system, and that's where you get the activeness or the passiveness of the scavenging system. Okay, and then these are some of the safety features to prevent giving hypoxic gas mixture when you're ventilating a patient or when you're using an anesthetic machine. And it's actually a summary of everything that we've talked about. So I won't go through that. I'll just leave the screen there. And this is the last slide, and I'll allow people to comment or ask questions.